All right, what's up, guys? Gonna do another video here. A little bit different today. Go ahead and cut the video and share screen here. So today, instead of recapping, actually just gonna walk you guys through um, just a coding calculation that I've got to do real quick. So turns out somehow I was doing uh, the wrong equation. I guess I was like using a version in the book that was like a reduced version, but that's not the version I was supposed to be using for my scattering equation. So what I'm doing right now is I'm just writing in what the equation that I'm actually going to code up is going to be. First thing I'm going to do is I'm going to code up this constant. Um, so we're going to do that, and then once I do that, I will show you all how I'm plugging it into my data and then give you a little bit of an insight as to what I'm doing. So basically, what I just did was wrote up uh, just for you guys to see and so I can see the equation I'm actually going to be doing. And so um, I've got to calculate this equation here for the constant z times z. Little z is the incident alpha particle, which is going to be equal to 2, which I'll write in a second. Big Z is the atomic number of tantalum foil, which is 73, which is all squared. That's going to be multiplied by E squared, which is the fundamental charge constant, divided by 4 pi epsilon 0, and that whole thing is squared. And the reason I did it like this is because it turns out this whole thing right here is a nuclear physics unit, which I learned today from Dr. Daniels, thankfully. And then this right here is just, again, just the kinetic energy, 1 over 4 times the kinetic energy of our incident alpha, which I will be plugging in again. And this whole thing, this whole constant is going to turn out to be in square femtometers. And so the first thing I need to grab um, is little z, which we're going to say is equal to 2. Big Z is equal to 73. E squared. So this whole thing, I'm just gonna write as nuclear. Well, actually, better yet, I'll just call it alpha, because that's actually a version of the fine structure constant. Um, so I'm trying to think what I could look up to get that value. I might have it written down. Check. Yeah, I do have it written down. So this value here for this whole chunk is going to be 1.433, or sorry, 439976. And that whole thing is squared. Then I have to do the kinetic energy. So KE is equal to 5.47 times 10 to the sixth, which is actually going to end up canceling because we're in this constant is an MeV Fermi. So the hashtag lets you write without it actually running as code, just for like little markers. These ones are unitless. Oh, sorry, int for integer, and then this is an MEV as well. So you'll see MEV cancels here with 1 over MEV here. Fermi stays. This is unit list, and then the whole thing squared, so we get Fermi squared. Okay, so now that I have all of those things, basically what I need to do now is just run the calculation. So what I'll do is I'll say uh, constant equals z times z, and we'll square that whole thing. And then I will do times alpha times 1 divided by 4 times KE. And this whole thing is squared. Just to make things easier, I'll just write that as what it is and square it here. Okay, so now this should give us our constant in square Fermi, or centimeters. Hmm, not sure if that's right. Hmm, seems right, I suppose. Um, okay, so now I'll go back over here and see where I actually calculated the cross section. So what I actually do is just okay, well the first thing I need to do is oops, sorry about that. First thing I need to do, move this. No, I guess not. Have to wait for it to move. So can you move? There we go. I'm just done. So minimize this. I need to convert this to meters squared or barns, but I'll go ahead and do it meters squared. So in order to do that, I need to multiply it by 10 to the minus 30. So, all right, constant underscore m is equal to constant times 10 to the minus 30. That'll put us in square meters. So then I'll say print constant underscore m. Oops, I'll do my fancy stuff here. Constant meters squared. And all I'm doing with this fancy parentheses stuff is it allows me to write text in front of the number instead of just printing a random number with no context. Uh, there we go. So now what I want to do is I actually want to plot. my cross section. But before I do that, I need to import NumPy and Matplot. These are just libraries that I'll need in Python to be able to do the functions I'm about to do, like the assign function and the actual plotting. So now that I have my constant, I can go ahead and say, okay, um, the actual cross section is going to be equal to the constant I have in meters times 1 divided by NP sine of theta, which I'll go ahead and put theta in here in a second. And that whole thing is raised to the fourth. Hence the double parentheses that I did here. Um, so now that I've got that, I've got to set up what theta is. So theta is going to be, we're going to make it an array ranging from 1 to 179. Number here, 100, just for plotting stuff. So the reason I can't do 0 and 180 is because that'll triple divide by 0 error in here. But it's going to give me what I need doing it this way because Python, I believe if you type in a 1, it runs from 0 anyways, but if you type in 0, it'll actually give it a divide by 0 error. So, uh, sorry, I'm a little sleepy, guys. I just wanted to kind of take you along for what I'm doing. So this is actually a conversion that I'll need because the NP sine function takes in values in radians. Call it theta rad, call this theta deg. So I gotta call this theta deg. Now this should um do what I want it to do, hopefully. Um, so what I'm gonna do before I plot anything, well, no, actually, I'll print it just to see what it's giving me. Name theta is oh, okay. So those are looking about what we need them to look like. So that's good. Um, it should be a little bit different than what I had here. If I was to go in and print this, yeah, it's definitely different. It's not a huge difference. So definitely it was necessary to recalculate it, obviously, but see how the graph changes. This one has a top end at 10 to the minus 19. Excuse me. This one we're gonna see. So we'll do plot, uh, plot.plt. That's gonna call what we need. And so now we're gonna plot theta deg on the x-axis and cross section on the y-axis. And we want line style to be that, and I'll make the color green since that's my favorite color. And I'll go ahead and put plot show, um, just to make sure it's plotting right before I format it. Main plot is undefined. Oh, no, wait a minute. Oh, that's why I did it backwards. It's PLT dot plot. Oopsies. Matplot, what did it pass now? Hello? Am I stupid? Oh, oops. I always forget to do that. There we go. Well, what the hell is that doing? No, wait a minute here. This is definitely something's going wrong here. Surely. Uh, See, this is what I want to do to this guy so you can kind of see what the process of this is, doing all the troubleshooting and everything. Uh, oh, duh. Gotta divide this by two. Is that gonna make that big of a difference? Yeah, it did. Okay, good. So the reason it looks like that, not pretty like our other graph, is because the other graph is a log scale. So I'll do that here in a second. But first I'm gonna label my axes. So on the x-axis, we have theta in degrees. On the y-axis, we will have cross section in square meters. And now I'll do plot dot y scale log. That should look nice and nice and pretty. There we go. Okay, so it's not a huge change. As you can see here, this one tops out at 10 to the 19. This one tops out at 10 to the minus 20. So it's not a huge change. However, it is definitely a change that was very important for us to make. Very, very important for us to make. So now that I have this corrected calculation, I can basically go in here and troubleshoot all this different data, sadly. But it shouldn't take that long. I don't know um, how much of that I'll take you guys along for. However, what I'm gonna do first and foremost is probably just gonna bring it actually over to here instead. Um, and I'm gonna go ahead and get rid of this for now, just to condense it a little bit. And so just for Dr. Daniels, I'll go ahead and run this calculation again in Barnes. And so the way that I'll do that is um, I'll say constant underscore B equals constant underscore M times 10 to the minus or 10 to the 28. So that'll convert us into Barnes. So I'll print that. And so now that I have that, I can go ahead and run this thing again. And now I'll just have to change that to a B. Say this is in Barnes. And there's my graph. So again, not that big of a change, just about a factor of 10. That's what it seems like, which isn't like horrible, but it's obviously important because this is a real life experiment. So, if I was working as a professional in an actual, paid job at a lab, a factor of 10 is, probably enough to get someone fired. So it's definitely good to troubleshoot those things. So what I'll do before I cut this off, because I'm gonna update you guys, um, probably tomorrow night when I get home, um, is I'm gonna look at other plots that I have that take into account the um, cross section that I need to use, which for one would be this, for sure, this right here. So now I'll come in here. And now all I have to do, because I'm putting it in this code, is do, 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 uh, oh yeah, remember I did like a fancy table thing. So we're gonna say, okay, so there's a few things I need to change here. I need to change the measured cross section in meters is grabbed here. So I ought to change that to underscore M. Change this one to underscore B. Go ahead and run those. And the reason I'm doing that is because in this calculation here, I can go ahead and get rid of this. And what I can do, I'm also going to capitalize these, differentiate them from the code up here. What I'm going to do is I'm going to get rid of these because they're not necessary because I already have them defined here. So now what I can do is I can just do a display table of cross section underscore M and cross section underscore B. Oh, PD is not defined. Where are you at? PD dot data frame. Ah, forgot I got to import pandas. There's that. So import pandas. Gotta love it. Wish I had a real panda. So, whoa, crap. Why is that giving me so many? What is it? Why is it running it like that? I did not ask for that. Hold on a second. This is, I don't understand why it's doing that. Why are you 3752? Sir, what's going on? Um, it's not. See, I don't need that because I've already calculated it. For some reason, it's spitting out this weird. Why don't I just make this a lens base? Error. Look, ran exactly the same. But see, what I don't understand is I'm telling it to loop through, starting at 3 degrees, going up to 75 in increments of 2, and somehow it's doing all that. Okay, well, instead of doing this fancy table that I don't really need, I'm just gonna basically uh just print my cross-sectional values from the above code. I don't need to get all fancy. As I backspace to capitalize things. Oh well, I'm OCD. So so this will just be cross section M because this is already ranging through everything. So I might as well just get it for everything. Um, And now basically I'm just going to copy this line of code. So a nice thing that you can do in coding is just tweak a few things, makes things go a lot faster. Okay. So there's my cross sections ranging. Okay, cool. And so that makes sense, right? Because it's starting at 1 and going to 179. And you can see on the plot here, I don't know why is this in, hold on a second. This should be, this is in meters. For some reason. What is going on here? This should be, why are my axes messed up? Uh, well, this is going on a bit too long. I'll get this cleaned up, guys, and I'll show you the full fixed data tomorrow's video. But thanks for watching along. Hope you enjoyed me struggling. So hope you have a good night. Bye, guys.